This is chapter 8 and 5, stability of first-order circuit. In this chapter, we will discuss about the stability of electric circuit first. The stability, but there are many definitions of stability. The Bibos durability and Lyapunov. We will learn about the stability in many classes. It's control theory, or the dynamics and other things. But generally, the stability, the most general, the definition of stability is Bibos stability. Stability, that means bounded input, bounded output. When there are some system here, there are some input and there is some output. When input is bounded, the output is bounded. In that case, we call the system is the Bibos stable. Generally, when you say the system stable, means the Bibos stable. In this chapter, we will discuss about stable. Then the stability, the definition of stable is a Bibos stable. Then here, we will discuss the natural response of first-order circuit here. The reason we discuss the natural response, not forced response, is stability is a characteristic of system, not input. I mean, the reason if there's some, the input is bounded in here, then the system, then output is not bounded. This is diverse like that. You can say this is unstable. Why output is unstable? That is not because of input. That is because of a system. So stability is a characteristic of a system, not input. So if this output is xt, is the sum of natural response and forced response. So because stability is a function, stability is a characteristic of system. So Fx is caused by the input, and transient is determined by the system. So natural response is very related to the stability. So if we want to check the stability, then you should focus on the natural response of the system. So we will discuss the natural response of first-order circuit to see the system is stable or not. So when we have a first-order circuit, the response is like that. Then generally x and t was k exponential minus 1 over tau t. That is a general form of natural response. So why? Because the characteristic of system is first order differential equation dt xt plus 1 over tau xt is 0. That is the natural characteristic of the system. So dt xt is minus 1 over tau xt. Therefore, xt is ke minus 1 over tau t. That's your general form of natural response. So if the tau is positive value, then x and t is k exponential minus 1 over tau t. When time is equal to infinity, that is equal to 0. Why? Because tau is positive, so that is a negative values. So it go up to the 0 when tau is infinity. That means x t is infinity, x and t is infinity plus xf t is infinity, because it go to the 0, so it will be f xf infinity. So stable. Here xn is go to 0, xn is vanishing. So this is stable because natural response go to 0. However, if tau is negative value, then x and t will be k exponential minus 1 over tau t when this is going to the infinity. So because this is negative, so total is a positive. So that is a positive, so it go to the infinity when t is equal to infinity. So then x t is infinity is xn infinity plus xf infinity. It is a constant value, but is equal to the infinity, so it will be infinity. That means not bounded, so we consider this is unstable. Because why? This is unbounded. So the system is stable or not is determined by tau. Tau is a characteristic of the system. Because time is determined by the parameters in the circuit in R and C or LC. So this is an example here. Example, we have the voltage source here, plus, minus, and one resistor and one capacitor here. So this is C and R, and this is the VT, and this is the VS. So I will solve this problem. VS will be, we define this is current, this I, then VS equal Ri plus V. Because of this capacitor we know that I and C dt dV. So we rewrite, there will be Vs is R and I C dt dV plus V. Based on here, we can derive the first order differential equation. V plus 1 of RC V equal 1 over RC Vs. So here we know that 1 over tau is 1 over RC. Therefore, tau is RC. So this is the element of the system in the first order circuit. R is resistor, C is capacitor. So both of them is positive values. So tau is positive, system is stable. Why? X and t will be k exponential minus 1 over tau t. Tau is positive values. So in other case, there are current source here, this inductor, and there are resistor here. It's L, R, and this is IS. We define the voltage here is V. So we know that V is L dTd IL. We define this is IL. And we can make a KCL here. Plus IS minus IL minus RV equal to Y, because this current is V divided by R. And I know the V is here, so we insert V there. Then IS is IL plus 1 over R. V is L dTd IL here. So we get the first order equation, IL plus R over L IL equal R over L IS. So we know that 1 over tau is R over L. Therefore tau is L over R. R is positive, L is positive, so tau is positive. Therefore stable. So if the circuit is consists of passive elements such like resistor, inductor, and capacitor, then system is stable. Why? In the case of capacitor and resistor, the tau is RC, positive value, so stable. In the case of LR system, the tau is L over R. This is a positive value, so system is stable. So in the conclusion, if the circuit is consists only independent source and passive element such like RLC, then system is stable. So in general, RC and RL circuit with independent source is stable. However, the first type circuit that contains op-amp or dependent source may be unstable. It's not always unstable, may be unstable. So we will do this some example such like here. The problem is the find capacitor voltage here. So we will do this simply here. Metro. Example 8, 5, and 1. Find capacitor voltage. Vt 4, T is positive. Here there are one capacitor, so this will be this circuit will be first other circuit. So at first, what should we do? We remember step first. What should we do? First, find initial condition. How can we do that? The solve the second, and when time is smaller than 0. And then what should we do? Next, we will discuss about the steady state. And third is find the K. There will be the sequence here. So we will do at first. Step 1, we'll find the initial condition. The when t is smaller than 0, the circuit looks like 12 volt and 5 kilo ohm. And there are dependent current source here. And because when t is 0, this is open, so no branch will register, and the capacitor here, and 2 microfarad, and define this current is IT, then there will be 2 IT here, this here, and define this is VT. Because source is constant here, so in the steady state, in the steady state, capacitor is open circuit. So they'll be open. That means there are no current here. 0 current, 0 ampere. So that means in the node of A here, the KCL, then plus IT minus 2 IT plus 0 equal 0. So what's meaning here? Minus IT is 0. Therefore, IT is 0. So we have initial condition of T, I is 0. In the steady state, because this is 0, therefore 12 is 5,000 and current I, this is voltage over here, M plus V. I is 0, this is 0, eliminate here, therefore V T equal minus 0 is 12 volts. This is the initial condition. Then next, what should we do? Next, we will redraw the circuit again. Then this is 12 volt here and 5,000 ohm, and there are also current source, dependent current source. This is IT, and this will be 2 IT here. Then because switch is closed at T is 0, so there will be some resistor here. This is 10 kilo ohm, and the capacitor here. It looks like that, and 2 microfarad, and this voltage is VT. We should figure out the value of the VT here. Then to make a simple the circuit, I will use the Thevenin theorem here. So I will make more small. Okay. And this is 5 kilo ohm. To make a simple equation, simple circuit, I will use Thevenin theorem. Based on here, I will make a Thevenin circuit of here. So at first we will find the open circuit voltage here. So there will be plus minus here, 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 and this is VOC, and here I will define this is IT, and this is 2 IT caused by current source here. Then this is 10 kilo ohm. Because of KCL here, this is IT, and this current is 2 IT. So this current should be IT here. So 12 is 12 volts. Then 12 the same is this is 5 kilo ohm, 5,000 and IT, and this voltage is 10 kilo ohm is IT. So this plus VOC, then VOC is minus IT here. So put the value here, 12 5,000 minus 10,000 IT here. So IT is minus 0.0024 ampere. Therefore here VOC is 24 volt. So we get an open circuit voltage here. Then there are the dependent source. We do not use the Thevenin resistor. We should find out the short circuit current here. So we'll make another circuit, 12 resistor, dependent source, and short circuit here. So this current is ISC and 2I. This is I. This is 5 kilo ohm here. So we make KCL in there. So plus IT and minus 2IT, and because this is short circuit here, there are no current, so minus ISC equal to 0. Therefore ISC is minus IT. Then because this voltage difference is 0, so 12 is that here. The 12 is 5,000 and IT. Therefore IT is 12 divided by 5,000 will be 0.0024 ampere. So ISC is minus I, so minus 0.0024. So here, based on here, we can calculate RT. Thevenin resistance is VOC divided by ISC is 24 minus 0.0024. That will be minus 10,000. Unit is ohm. So the equivalent resistance, the Thevenin resistance is minus 10,000. So we can redraw. There is a open circuit voltage VOC is 24 volt and Thevenin impedance is minus 10 kilo ohm, and there are capacitor here 2 microfarad. This is the VT. So we can solve this circuit here. It's simple. VOC is, we define this current is IT plus VT, and I know IT flowing through the capacitor, so IT is C dt dVt. And then we insert that is here, so we can rewrite this first set of equation is dt dVt plus 1 over RTC VT equal 1 over RTC VOC. So here we can get the VT will be VNT plus VFT. VNT natural response, the FT is the forced response. So when the system is infinity, then what is the VFT? When system is infinity, then the capacitor is an open circuit, so no current, so that will be source, the 24. So VT will be K exponential minus 1 over tau, and tau is RTC, T plus 24. So because tau is here, there will be K exponential RT is 10,000 minus 10,000, and capacity 2 microfarad. So RTC is minus 4 to 10 minus 6 will be minus 2 here. So that value is positive 50 T plus 24. So to find out the K, what should we do? We have to use initial condition over here. When T is 0, that value is 12. So V0 equal K plus 24 is 12. Therefore, K is minus 12. So complete solution of VT is minus 12 exponential 50T plus 24 volt. So when T is infinity, this 24, but this is go up to infinity because 50, so that will be 50. Actually, this is minus to minus infinity. So you can say this is unstable. So in the case of such like the dependent source, it could be unstable. But in some case that could be it could be stable even though they have a dependent source. It depending on the circuit configuration. So if we have circuit containing the dependencies or OPM, then you should check the system is stable or not, and then step by step. The way to check the stability is tau is positive or not. Tau is positive, then system is stable. Tau is negative, the system is unstable. Just simple the checkpoint to find out whether the system is stable or not. Next chapter is unit step source. I mean, we have some new definition of unit step. The unit step we will discuss in maybe the engineering mathematics, the unit step when you study Laplace. But we'll leave you again the unit step definition of the unit step. A unit step function means abrupt change in the voltage or current here in this way here. The expression of a unit step is ut is 1, 0 when t is smaller than 0, and 1 when t is larger than 0. This is a general definition of unit step function. So more general form is ut minus t0 means this is 0 when t that value is negative, that means it's more than t0. 1 t is larger than t0. This is a general the unit step definition. Oh, I'm sorry, I have long here and here. When t is 0, then ut does not is not defined here. So I'm wrong. So when t is smaller than t0, then this is 0, larger than t0 is 1. When t is t0, not defined. Fine. So this is example when the unit step function is applied to the voltage source here. So voltage source looks like that here. That means this is time t, and there will be t0. Then before the t0, because this is 0, so that waveform is like here. This is A. Then after t0, then it going on here. And so this is A plus B. So this is this is a unit step voltage source example. So as you see, it looks like a kind of a step change in the circuit when you insert the switches. The same effect on the electric circuit. So we usually use this unit step function to model the step change in the circuit. This is another example. We make these stepwise the waveform here. Then how to implement of that? It's quite simple. Actually, this is a sum of this waveform and this waveform. So we add in here, if we add this again, then this is a 0 and adding here, so this is like that, and here that they cancel here, so it looks like that. So what is this? This is u, actually it's not u, it brings to the v0, so v0 multiplied by u t minus t0, and this is minus v0 and u t minus t1. So we read it in here, so this is v0 u t minus t0 minus u t minus t1 here. This is a kind of a general expression of this waveform. That will be written here. So 0 when t is below t0. This is the v0 when t0 t1 is 0 again. T is larger than t1. Can we express this waveform in log graph here? Then we want to do this, draw the symbol in the circuit. Then there are two sources here, so we can draw here looks like that. Here there will be v0 u t minus t0, and there will be minus v0 u t minus t1. We can draw, there will be terminal is vt. So we can draw this, the stepwise function over here. So in case we call this is a pulse, the signal, pulse value. So that is a definition of that is constant, the non-zero, the value for time duration delta t is t1 minus t0. So we call this waveform as pulse signal or pulse voltage or pulse signal. And here. So we can solve this source with the same sequence when this looks like a kind of the switches. So we'll give example here. This is example. And we'll find the current IoT. This is example. This is example 8.61. Okay, we will do this at first. So Vs is the unit step functions. So we rewrite the Vs is when t is smaller than 0, so there will be 0 is 4. But t is larger than t, then there will be minus 4. So at instance of t equal to 0, there will be step change. So we need to check in the time division here. T is 0, time t, then this is another circuit 1, and there will be circuit 2. Circuit 1, circuit 2. So first we draw t is smaller than 0, then there will be source. How much is it? This is 4 volts here, and resistor 20 ohm, and inductor here, so 10 Henry. And we define this current IoT. So here the reason we discuss over here is we want find why we analyze this condition, because we need to find initial condition. So we assume that this is a steady state. So when the DC system, all sources DC, the capacitor is open and inductor is short. So there will be rewritten here. This 20 so 4. This IoT is 4 divided by 20. So there will be 0.2 ampere. So I0 to minus is 0.2 ampere, and there will be initial condition. Then what should we do? We find the new circuit when t is larger than 0, then what is changed? The Vs changed it 4 to -4. So we redraw the source here. It's same resistor, same inductor here, but this voltage is -4 volts. So there will be 20 and 10 Henry here, and this is I0t. So what should we do? We should make a differential equation from the circuit. So this is -4 is same with the defined I0 current to flow here, 20 I0t plus the Vt. Based on inductor, we know that Vt is L dTd I 0. I will rewrite it. This is R. This is R. So we rewrite -4 is L I0t plus L dTd I0t. So we make equation R is 20, L is 10. So dTd I0t plus 2 I0t equal -0.4. So here we have a first order differential equation. So we are ready to get the complete solution of IT. I0t will be I0NT natural response plus I0FT forced response here. Then first, what is IFT in t go to the infinity? And because this is a constant, so the same way inductor is short circuit. So there will be 20, let's say 20, and voltage is -4. So there will be -0.2 ampere. So this is the first response. Then we can make a general form of k exponential -1 over tau t minus 0.2. Then what is tau? I mean here, 1 over tau is the same with 2. So we adding the here, there will be k exponential minus t tau minus 0.2. So what is the remain here is k. How to solve the k? Using initial condition. I0 is k minus 0.2. There will be 0.2. Therefore, k is 0.4. So here, I0t complete solution over here is 0.4 exponential minus 2t minus 0.2 ampere. So this is a complete solution. You can redraw when t is smaller than 0, there will be 0.2 ampere. And when t is less than 0, there will be minus 0.2 plus 0.4 exponential minus 2t ampere. This is the general solution for the first order electric circuit. The source is consists of the unit step functions. There is another example over here, is the similar things. So we will solve this problem again. It will be more simple because we know the solution over here. So why is that? Because the capacitor voltage we need here, and there's a voltage here. So what should we do? then we need to make a simple this circuit. How can you do that? Maybe we make a Thevenin circuit here first here. So to make a simple, I will like to divide this circuit here. So we like a more simple circuit here. Yeah, we'll do that later. So anyway, the Vs here, Vs is 7 minus 14 ut. So based on this t equal to 0, there's another source 1, and this is another source 2. So Vs will be 7 when t is smaller than 0, then minus t when t is less than 0. So at first we should check the initial condition over here. So we'll element first here. What the first thing is, find initial condition. Then there will be source, register. Because this is the state, this will be open. Because capacitor is open, it will be this. So in this area, t is smaller than 0. The source is 7, so it will be 7 and 3 and 5. Here, VO is 3 plus 5, so 7. And that will be 35 over 8. That is a initial condition here. So V0 t equal minus 0 minus is this is initial condition. Then we'll do this second step. Second, we need to check the t is larger than the 0. Then what should we do? I told you at beginning, I make a simple circuit with the Thevenin theorem. So this is Vs is minus 7 and 3 and 5. Then this is the VOC here. So VOC is 3 plus 5 minus 7. So that will be minus 35 and 8. The next thing is we will discuss about the RT. This is short 3 and 5. This is RT. So RT is parallel of 3 and 5. There will be 1 over 3, 1 over 5 inverse. So 15, 5, 3 inverse is, that is it. So we can redraw the voltage source here is minus 35 divided by 8, and RT is 15 divided by 8, and we have a capacitor here. This is 460 millifarad, and this is VT here. So we can get it. VT is VNT plus VFT. Then VFT is a state, it means final, the state, the voltage here. So because this is state values, then source is here. So VF infinity will be, capacitor is open circuit, so that voltage is same with that voltage here, minus 35 divided by 8. So VOT will be K exponential minus 1 of tau t minus 35 divided by 8. Then we need to check it. What is tau? We know that tau is, in the case of RC, we already know that there will be RC. So what is R? R is 8T, and capacitor is 0.46. So we can use it. We can use it. Then there will be a little bit complicated, but there will be 34.5 divided by 400. Generally here. So we can rewrite here VOT is K exponential minus 40 divided by 345T minus 35 divided by 8. Oh, divided by 8. Then we remain the K. How can get K? Using initial condition here. V0 equal 35A is K minus 35. Therefore, K is that values. So we insert K in here. So final response of that is V0T is 70 divided by 8 exponential minus 403.45T and minus 835 and volt. This is a solution of this, the voltage T. As you see, in the case of the Foster circuit, there are two kinds of things, RC or LC. So we already make even though there's a more complicated system, we make a simple Thevenin circuit like that. Then other solution is very fixed. We can get tau is RC, and we can calculate the force response, because this force response, in the case of the voltage source is a constant, then we open circuit. So we can simply get the state response, the force response here, and we know the tau is RC. Then using the initial condition, you can get the K. That's it. That's the general approach to solve the first circuit here. It's very simple. It's not complicated anymore. Then until now, we have discussed about the circuit that the source is a constant. The reason we deal with constant source is that is a simple. So we discussed about that here we will discuss about the other source, in non-constant source case. So there is response to the non-constant source. In conclusion, I will give you a conclusion here. Even though in the case of 7 2 the source. Actually, our response with xt is xnt plus xft. That is a response of system, and that is a response of input. So when the input is different, then there will be change of that here, and this is now change, and this is defined by system, and this is defined by input. So when input is non-constant, then there's effect only here, not there. So we will discuss about only here. The differential equation given by RL or RC is the general form of A is dTd xt. X could be current or voltage, and AXT equal to YT. And here maybe A will be 1 over tau. Now this is the form of first order differential equation, and when we have first order circuit RL or RC, then we get this simple, the general form of differential equation. Then using the integrating factor method, which consists of multiplying differential equation by factor that make the left side here, left side perfect derivative. That means like here, we make dTd xt plus axt here, and we multiply here is exponential 8 here. Then there will be yt also multiply eat here. This is a, the same a here. Then what happened here? We do that is then dTd xt. Okay, we will display again dTd xt and eat plus axt eat here. That will be same as dTd xt eat plus a is here, xt ae 8 here. Then it will in d okay dt d xt e 80, this is same, and this is xt, and this can be rewritten here. They'll be same with dtd e 80, the same. So that and that is the same with dtd xt e 80. So this term can be rewritten here, dtd x exponential at equal to here y e 80. Then what do? We will do integration. Then we integrate here and integrate here about dt and dt. Then, because there is derivative and integration, so the result is Ch08 equal to integral y(E)at dt. So plus, because we have a derivative integrate, there will be some the k. So xt will be divided by here exponential minus 18 integral y(E)at dt plus k exponential minus 80. That will be general solution of first order differential equation. So based on here, we can do many things. We copy here because we have very here. So we will do this first let yt is m. Why is that? This is a case of constant source. So we apply the m here. So xt here, xt will be exponential minus 80 integral y is m, so this is m exponential 80 dt plus k exponential minus 80. Then we'll do this here. That is exponential minus 80, because it's constant, it will go out of the integral minus infinity tau, not tau, this t exponential a tau d tau. There will be exponential minus 80 and m. There will be 1 over a exponential a tau minus infinity t. But generally the a is positive values, so there will be 0. So there will be exponential minus 80 m 1 over a exponential a t. So that is eliminate each other, so result will be m over a. So therefore xt is m over a plus k exponential minus at. So that is xft and that is xnt. So xft is constant when yt is constant. Then next, we'll do this. For example, let yt is an exponential value like ebt. This is exponential form. From here, we will do this. B is negative value y. If b is positive, then when time is infinity, there will be go infinity. There is an infinity input we will discuss about here. So assume that b is negative here. Then the same way we will do this here. xt is exponential minus at integral. We have y here. The y is ebt. ebt exponential at and dt, and plus k exponential minus 8. Actually, this term is a natural response here, so we don't care about here. Anyway, so we reuse only that term here. So there will be exponential minus 80 integral ebt exponential 80 dt here. Then there will be exponential minus 80 integral, actually is tau here, minus infinity to t exponential a plus b tau and d tau. So there will be exponential minus 80 1 over a plus b exponential a plus b tau minus infinity to t. Then a should be larger than the b, will be positive. Then we assume that there will be a plus b exponential minus actually this is plus bt here. So xt, therefore xt is 1 over a plus b exponential bt plus k exponential minus 80 here. So when the input is exponential here, then force response is the same form, bt. So this is the exponential form. So this is very important here. So as a result, and with the cover here, we will cover these contents. So this is a result. When constant force response is constant, then force response over here is constant. When the exponential, for example, ebt like that, they're the same way, but again it's different. If there are sinusoidal like m sine omega t theta, then ft is also the general form of sinusoidal, a sine omega t plus b cosine omega t. Important thing is this is omega and this is same omega in here. That is a result of the case of non-constant source. So natural response is the same. We deal in the previous chapters, and only difference thing is the forced response in the case of the forced circuit. Okay, this is example we'll do here. First, we will do the This is example. 8.71, find IT here. So this is the same way, because of the switch here is there'll be some step change over here because of switch, and the switch is open at 0 point, at t is 0. So we have to get the when t is small than 0, then circuit looks like here. This is voltage source here, and this register, because when t is smaller than 0, then this is source circuit here, it's closed. So 5, and then this is inductor here, and this register here, and there are the voltage source here. So here, when you check it, that is Vs here. The Vs is 10 exponential minus 2t and ut here. What's the meaning of here? When t is smaller than 0, that value, because of ut, there is 0. And t is larger than 0, there will be 10 exponential minus 2t. So in case of here, for t is smaller than 0, there is always 0 volt here. So what is the meaning of here? This is 0, that means this is like a short circuit here. And this is a 4, and this is 10 volts. So there are only constant source. So in this case, the inductor is a short circuit here, 0 volt. So in this case, IT in 0 minus is 10 divided by 5. So this is 2 ampere. So this is a initial condition. Next we need to figure out the circuit when t is larger than 0. Then at this point, switch is open. So this voltage source does not make an effect to the source. So this is open, so 5 ohm, there's no effect to this limited circuit. So this is not used anymore. So circuit is more simple. Only inductor here, and resistor here, and source here. So 1 Henry, then this is 4 ohm. So this is 4 ohm. So we define the name of current is IT, and we define this voltage as VT here, and Vs is 10 exponential minus 2t here. So we can make a differential equation here. So we define this IT in this here. So this is Vs. So this can go into the I here. So Vs is the same with 4 and IT plus the Vt. Then from here, we know that Vt is L dTd IT, and IL is 1, so this is dTd IT. Replace that here, so dTd IT plus 4 IT equal to Vs. What is Vs? Vs is 10 exponential minus 2t. This is the differential, first order differential equation of this circuit. So based on here, we can get the general solution of the IT is INT plus IFT here. So at first, we need to check out what is IFT. Then IFT means let, because source is an exponential function. So we make a IFT is a general b exponential minus 2t. Why? The source is looks like here. So we can use the general form of the IFT. So we insert that this IFT is the general differential equations. So dTd IFT plus 4 IFT should be 10 exponential minus 2t here. So dTd b exponential minus 2t plus 4b exponential minus 2t go to 10 exponential minus 2t. So we deliberate that values minus 2b exponential minus 2t plus 4b exponential minus 2t should be 10 exponential minus 2t. So 2b equal to 10. Therefore, b is 5. From here, we know first response is 5 exponential minus 2t. We got it here. And then the main thing is IT is natural response. Its form is same. K exponential minus 1 over tau t and plus IFT is 5 exponential minus 2t. Here, this is the general form of that. So tau is that values. So we know that 1 over tau is, from here, 1 over tau is 4. So we can rewrite here is k exponential minus 4t plus 5 exponential minus 2t. The remaining thing is k. How can get the k? Using first order, initial condition over here. Initial condition is 2 ampere. So I0 is 2 is k plus 5. Therefore k is minus 3. So our complete solution is IT is minus 3 exponential minus 4t plus 5 exponential minus 2t when time is 0. And t is 0, then based on here, we know it's 2 ampere. So that will be 2. So this is a complete solution of the current in this circuit. This is another example here of the similar things, but the source is, in this case, is sinusoidal value here. The step is the same to solve this equation, but we will do this with time. So we copy this circuit and copy. And this is number example 8.7 to find the voltage VT here. And in this case we have some condition over here. The V0 is 0 and is is 10 sine 2t and ut like that. This ampere here. This is the given condition. Wow, it's great news. What is that? The initial condition of there is given, so we don't need to care about the initial condition. So this thanks. If we don't have this condition, we should make the initial condition, but because the condition is given, so we don't make step 1 to get the first initial condition here. So we don't need to figure out the t is smaller than 0. You don't need to do that. Then we'll use step 2. T is less than t. Before that, we need to figure out the source. I mean is, because you're using the unit step functions. There's a 0 when t is smaller than 0. But there's 10 sine 2t when t is less than 0. So we don't need that. We just given the v0 is 0. There will be initial condition. Okay. Then next we will do here when t is less than 0. The source is same because the source is a unit step functions. This is current source here and capacitor and the register here. This is 4 and we define the that is Vt and we define that current is It and capacitance is 0.5 farad and this is Is. So what should we do? To make a first order differential equation, we can use the KCL at this point here. The KCL, then plus Is minus It minus Vt divided by 4 equal to 0. Why? This current is Vt divided by 4. Why? This voltage defined Vt here. Then I know that characteristic of capacitor, the It is C dTd V, because C is 0.5, so there will be 0.5 dTd V. So we insert it here. Then differential equation Is minus 0.5 dTd V minus 1/4 Vt equal to 0. So based on here, we can make a general form of differential equation. dTd Vt plus 1/2 Vt equal to 2 Is. 2 Is. Is is looks like that, so that will be 20 sine 2t. So based on here, we can gather Vt complete solution here is sum of natural response Vt plus forced response here. Then first we should get VFT here first. A VFT is determined by the source. The source is sinusoidal, so we can make a general form of VFT. Forced response is A sine t, but the frequency is the same. 2t plus b cosine 2t. This is general form over here. Then how to get the A and B? It's very simple. insert Vt is here. So dT dVft plus half Vft should be 20 sine 2t. So apply here, then we insert that here, then 2a sine will be converted to cosine 2t, and cosine converted to minus sign, so minus 2b sine 2t plus half a sine 2t plus half b cosine 2t. I will make a simplify half a minus 2b sine 2t plus 2a plus half b cosine 2t is the same with actually that will be 20 sine 2t. From here we got it, half a minus 2b should be 20, and here 2a plus half b should be 0. So based on here, a is 40 divided by 17 and b is minus 160 divided by 17. That's your result over here. Okay, we can check it. Okay, 2 is 8 is okay, and 40 and 30 is right. We need to check it. 1720 equals plus minus. Okay, that's right. Okay, that's right. We got a solution here. So our VFT is 40 divided by 17 sine 2t plus minus 160 17 cosine 2t here. It's quite complicated, but it's not difficult. So the remaining thing is natural response. We know that Vt is k exponential minus 1 over tau t plus that 40 sine 2t minus 160 cosine 2t here. Then how to calculate the tau? We know that. What's tau? You know that here, because this is the thing is that 1 over tau is that values. The 1 over tau is 1 over half, 1 over 2. So the same thing is value 1 over 2. You change it. So remaining thing is the k. How can you get the k? Based on initial condition is 0. So V0 is 0. That means k is 0. So minus their values. Therefore, k is 160 over 17. So our complete solution Vt is 0 when t is smaller than 0, or there will be exponential minus half t plus 1740 sine to t minus 17 over 60 cosine to t. Then t is less than here. That is a complete solution of this problem. So the different thing is you need to find out VFC, but the force response is the same form of the input. So input is constant, that will be constant. Input is exponential, then the force response is exponential. The input is sinusoidal, then force response is sinusoidal in this way here. So other thing is the same procedure. So that's a way how to solve the first order circuit in the case of RL or RLC. Summarize, if you have to complicate the circuit, then you need to simplify RL or RC circuit using the Thevenin. Then you can choose the general step to get the complete solution of first order circuit. That's the way solve the problems.